All right, so this lecture will be an example of how to calculate horizontal shear flow within a cross-section. Last time we sort of derived this VQ over I equation, and we're going to sort of show you how to apply it here. So what we have is effectively a timber I section. So all of these, both the light blue and the light green there, are all, you could think of them as 2x8s or some sort of, lumber. And then we're connecting these guys by driving a nail from the ends into the web, just like that. All right. So that's our sort of structure. And the big question here is, well, how many nails do you need to use, right? Or how do we calculate how much force each particular nail has to take, right? So what we have, this cross section, you see all the dimensions there. The key over here is that we're going to evaluate this for a nail spacing of 25 millimeters, right? So what that means, I'm going to redraw this a little bit here, and this guy, and then I'll just show you that that's not the entire beam. So this is sort of an elevation side view of the beams, or the beam. And to sort of highlight that, let me just color this guy in green. All right, oh. I don't know why that's not working. Oh, I know why. Sorry about this. So this guy is the web here. Like that. And then these guys here are the flanges. And so really what we're looking at is this spacing here. Draw the ones on the bottom as well. So that spacing there is 25 millimeters. So that's what this 25 millimeter refers to. It is not the spacing within the cross section drawn over to the left. It's actually the longitudinal spacing. So if you look along the beam, how often did I have to drive a nail? Okay, so that's the situation. And basically what we want to do is we want to calculate the shear flow across that section right there. Right, that's where the nail is tying those two pieces together. Right. And because of that, that's where the cross-section wants to slip, right? Because there's nothing, there's no glue, there's no nothing. These sort of wood sections are just sitting adjacent to one another. We've driven a nail across that sort of shear plane, if you will. And we've got to calculate how much force needs to be transferred per longitudinal dimension, right? Per millimeter, per meter, however you want to do it. And then once we've calculated that, we can figure out, okay, if the nail spacing is 25 millimeters, how much force, how much shear force should each nail have to take, right? Okay, so this is, this is where we want to calculate shear flow here. Right now, it is exactly the same in this case as the shear flow across that bottom piece, right? So this is a symmetric cross section. So as you'll see, the numbers will work out. But if I calculate the shear flow between the top flange and the web, it will be exactly the same as the shear flow between the bottom flange and the web. Okay, so a couple things we've got to do here. We've got to identify the neutral axis. In this case, it's pretty straightforward because, again, it's a symmetric section, right? So that's our neutral axis. And then the height of the section that I want to calculate the shear flow across, I need to know how high that is above my neutral axis. So this is 50 millimeters, like that, okay? And this guy here, let's see. We're going to call that D. All right. So that is our D. All right. So this guy here, let's see. Well, let me, I guess, just start by writing the expression here. So this is Q, that is shear flow, equals VQ over I. Right? So this is shear flow, and that is force per length, right? That V is shear force. So that is the vertical shear force on the cross section, right? That's given up here as 500 newtons. Right? Q is the first moment of the area. And I'm going to say above the section where we want shear flow. And then I is the moment of inertia. And this is of the total cross section. So you can go back to the previous the previous lecture and sort of see where all of this comes from, right? So VQ over I is what we need, and the Q is going to be associated with this section here. Right? So this guy we're going to call area, right? So we've got this area and we've got this D. Right? So Q is just A times D, right? It's the first moment of the area, so I only have one moment arm. If you remember the moment of inertia, we actually have to add on those AD squared terms, and the D is squared because that is the second moment of the area, right? Okay, so let's go ahead and start calculating this. Basically, all we need is to calculate Q and I. V is given, and then we can calculate little q, the shear flow. All right, so let me go to blue. So Q is just that area times the distance. The area is 100 millimeters times 20 millimeters. Right. That is the area of that top flange, right? The 100 millimeter width, 20 millimeter depth. And then my moment arm is 50 millimeters plus 10 millimeters, right? So that is, that is this D right there. Right? Okay, so I work that guy out, and it turns out to be, there it is, 120 times 10 to the minus 6 meters cubed, and you can see I also did a unit conversion there. It would come out in millimeters, right? But just to try to keep everything consistent, I'll just move it to meters. Right? You can keep it in millimeters if you want, not a big deal. Okay, so that is Q. Then we also have to solve for I, right? So this guy would be BH cubed over 12 plus our AD squared term, right? In this case, we've got 20 times 100 cubed divided by 12. So that's the web, right? And the centroid of the web is the same as the centroid of the overall cross section because it's symmetric. So there's no AD squared term there. And then we're going to have two flanges, right? So I'm going to multiply this by 2. That's 100 times 20 divided by 12. And then I'm going to add my AD squared term, right? Which is 100 times 20. You know what? This is 100 times 20 times 60 squared, like that. Okay? So those are our two flanges. Right? So we work all of that out, and the moment of inertia here is 16.2 times 10 to the minus 6th meters to the 4th. And I will box that in red. So again, I'm just switching everything to units of meters. The key here is that because Q is the first moment of the area, it's in length cubed units. And obviously, moment of inertia is in length to the 4th because it's the second moment of the area. Right, so now we're ready to plug in. So I get my shear flow, did it again. I get my shear flow equals VQ over I. The V is 500 newtons. Right, my Q is 120 times 10 to the minus 6th meters cubed. And then my I is 16.2 times 10 to the minus 6th meters to the 4th. And when you work this out, you will get that Q equals 3,704 newtons per meter. So I am going to box that guy as well. So that is my shear flow, right? So every meter of length, right, I need to make sure that the nails transfer collectively 3,704. And this is important. It's not both nails, right? So it's not this nail plus that nail, right? Because we are calculating the shear flow only across, how do I want to do this? Only across this location, right? That is where the shear has to be transferred. So that top nail has to transfer 3,704 newtons every meter, right? So if these nails spaced at 25 millimeters or 1 inch on center aren't good enough, I'm either going to have to go with bigger nails, I'm going to have to change the connection. I can put angles maybe, on the outside here, and bolt through. There's a lot of different ways you can connect these elements. But I cannot, if I don't make sure that I transfer this 3,704 newtons per meter, what I'm going to get out of this cross-section is what I'm going to call non-composite behavior, and I'll describe that in a second. But basically what it means is that the assumption that we make that this cross-section behaves as a single cross-section with linearly varying strain across its entire height is not true, right? You have to make sure you're transferring shear between all the elements to enforce that linear strain distribution, right? So I'll get to that in a second. Just to be clear, this 3,704 newtons per meter. This is per, let me get rid of that pink. This is per shear plane. So the top shear plane has to transfer all of this, right? So we'll make a note that now, well, let me go back to blue because this is not the solution here, okay? All right, so now every 25 millimeters we have a nail, right? So the force in the nail, which is what we're trying to calculate here, is just the spacing of the nails, right, which is, sorry, 0.025 meters, right, times the Q. In this case, that's 0.025 meters times 3,704 newtons per meter. And now the F nail becomes 92.6 newtons. So every nail, top or bottom, right? Because if you calculate, and I'll show this in a second, but if you calculate Q, you will also get that it is, that you get the same Q whether you're looking at that top cross section or the bottom cross section, and so the shear is exactly the same. It actually turns out to be a different sign, so it's negative, but it doesn't matter. Again, shear, whether it's positive or negative, the connection, the nail is going to behave the same, right? The difference is that you could argue that Q should be negative because that D distance is downward, right? But as far as I'm concerned, you can always take D as positive, and that will still give you the proper Q. Okay, so that's our force per nail. So let's take a second here and talk about what would happen to this cross section or a similar cross section if we do not have those connections. So hopefully what you see is that what the role of these nails are, right? So if I'm going to do this guy in blue, so if I just put two boards on top of one another, right, like this, so that's my cross section, right? And I simply support it, right? And let's say I add some sort of load here in the middle, right? What's going to happen if I bend this is it's going to bend something like this. I'm going to do my best to draw this, not, completely sort of bastardizing the deformed shape here, but it's going to look something like this. I didn't do a very good job there, but you get the idea, right? The point is there is a slip. So there is a slip between these elements, right? So this guy wants to go that way relative to this guy who wants to go that way, right? And if I were to look at the stress distribution here, right? So let me, I guess, do this in black. So let me take a section like that. If I were to look at how the stress varies here, it would look something like that, right? So each element here is on its own, right? So the moment of inertia of this cross section here, I guess I'll do it in blue. So I total equals I1 plus I2, right? So if this guy is I1, and this guy is I2, right? They do not have an AD squared term because they each have their own neutral axes, right? So they're bending separate from one another. Right? This is what we refer to as non-composite. So that beam, right, is basically just the sum of its parts. Right? There's no additional sort of synergy that you get between these elements. Right? However, if I'm going to redraw, right, basically redraw this same beam, right, and now what I'm going to do is instead of just setting them on top of one another, right, now what I'm going to do is I'm going to drive some nails into these guys. Right, so now I'm going to connect those boards together. Right? Now what happens is if I look at the deformed shape, right, it's the center line of the cross section that where the neutral axis is now. So it looks something like that, right? And now I can do a third one here, right? So that's how it bends, right? And here's the key. There is no slip. There's no slip between these cross section, right? Why? The reason is those nails are not permitting that to slip, right? So this is what we refer to as composite action. Okay, and now if we were to look at a cross section, the stress of this cross section now, let's see, it would be like this and like that. So now the stress looks like this. Now, I'm drawing it so it sort of looks like it has similar magnitude. Turns out the stress goes way, way down for a composite cross-section, right? Why is that? Well, it's because the moment of inertia is so much more, right? So now I will say that I total is much, much greater than I1 plus I2, right? Basically what I'm doing is I'm picking up a d squared term for each one of these beams, right? So that AD squared term that I don't have up here, right? Because each one has its own neutral axis, so their local centroid is at their sort of global cross-section neutral axis, right? This one, we only have a single neutral axis, right? And it's right in the middle of the global cross-section. So that's two neutral axes, and this is a single one, right? So for the purposes of this class, a lot of these examples are basically going to be, okay, here's a cross-section. Tell me how much force is required to impose composite action, right? That would be how many nails do I need to enforce this type of behavior versus that type of behavior, right? And admittedly, right, these types of behavior are extreme, right? So they're sort of the bounds. And you can put partial connections in there, and you could envision some sort of stress distribution that is in between these, right? We're not going to deal with that, but there is, there are some beams that are in fact designed to be partially composite. And, if you get into, decide to go into graduate school for structural engineering, you will also deal with that. But for the time being, we're going to just deal with either non-composite or composite action. And just to go back now and revisit this example in light of that, the question here, if what we're trying to do is calculate how much shear force is in each nail, basically the question could be posed, do the nails have enough capacity to enforce composite action, right? And if I tell you that a nail's capacity is 80 newtons, right, that is the acceptable force level for each nail to transfer, 80 newtons, right? So you would walk through this calculation and you would find that, the final the final force, right, in each nail is 92.6 newtons. Well, now I got myself a problem, right? Because I just told you that each nail can only handle 80 newtons, right? So again, I have some options. I can use more nails, although 25 millimeter 1-inch spacing is very tight already. So I might not be able to get away with more nails. I could use sort of clip angles to more solidly connect the flange to the web. I could bolt it, right? There's a lot of different things you could use. Regardless of what you use, this is the amount of force that needs to be transferred every 25 millimeters. Right? So that's sort of a connection design problem, again, to enforce composite action versus non-composite. Okay, that is it. I will talk to you guys later.